definition for the elementary row matrix. A matrix obtained from the identity matrix by a single elementary row transformation is called elementary row matrix. So, for example, let's take the identity matrix to be as 3 by 3. So that is 1 0 0 0 1 0 0 0 1. This is your 3 by 3 identity matrix, and let's apply a row operation on this matrix. Suppose I'm applying the row operation as E12, that is interchanging the second and first row. Just replace the first row by row 2, we get 0 1 0, and replacing the second row by row 1. So this is 1 0 0. So this is your elementary matrix obtained from this identity matrix. Suppose in another example, I am applying the row operation as E3 lambda. Lambda is any real number, right? So let me multiply the row 3 with lambda. So first row and second row will be as it is. I am just applying the operation on the third row. So third row becomes 0 0 lambda. In the next example, I am applying the row operation as E2 3 lambda. Whatever number be present over here at the first position, we are going to change that row. So I need to change the second row, R2, and I am applying the operation E2 3 lambda, which means first multiplying this third row with lambda and then adding this to the second row. So multiplying the first element, that is 0, with lambda, you get 0, and then adding this value to the first element of the second row of the identity matrix, that is 0 element. So 0 plus 0 gives us 0. Multiplying the second element of row 3 with lambda gives 0, and adding this to the second element of R2 of I3, that will give plus 1. So this is 0 plus 1 is 1. Multiplying the third element of R3 with lambda gives lambda, and adding this to the third element of R2 of I3 matrix, so that will give, yes, lambda plus 0, that is lambda. So this is how we obtain the elementary row matrices from the identity matrix, right? Okay. Second, the same as with the column matrix. So the definition for the elementary column matrix: a matrix obtained from the identity matrix by a single elementary column transformation. So we are going to apply the column operations now on the identity matrix is called elementary column matrix. For example, this is your identity matrix I3. Let's take this 1 0 0 0 1 0 0 0 1. So this is your identity matrix. So now I am going to apply the column operations. So the examples of elementary column matrices obtained from I3. Okay, I need to get first column matrix by applying the column operation, and let me denote that with F. So F12, what does this means? Interchanging the second column with first column and first column with second column. So I'm going to interchange the columns 1 and 2. So I get 0 1 0 and 1 0 0. Third column as it is. Right? Okay. In the second example, I'm going to apply the column operation as F3 lambda, which means I'm going to multiply lambda with third column. So the first column is as it is, second column is as it is, and third column will become, just multiply the elements with lambda. Multiply the elements of the third column with lambda. So we get 0 0 lambda, right? Okay. And then I'm going to apply F2 3 lambda. Please remember, if you have written 2 over here, which means you are going to change the second column, right? So the first column and third column are as it is. We are going to change the second column by applying column operation as just multiply the third column with lambda, right? And then add this value to the second column. So we get just multiply 0 with lambda, that will gives us 0, and adding this 0 to the 0 you get 0. Multiply the second element of the column 3 with lambda gives 0, and adding this to 1 gives us 0 plus 1, that is 1. Multiplying this third element of the column 3 with lambda gives us lambda into 1, lambda, and adding this to the third element of the column 2 gives lambda plus 0, that is lambda. Right? So this is how we obtain the column matrices, right, from the identity matrix. Let's move on to the theorems, and before that I'm going to discuss few things over here. What is singular and non-singular matrix? You take any square matrix, let's say A to be as 2 by 2 matrix. Suppose you take A to be as any 2 by 2 matrix. Suppose this is A11, this is A12, and this is A21, and this is A22. This is your 2 by 2 matrix A, right? Take the determinant of this matrix A. What is the determinant? Okay, let me write this as simply A, B, C, D. What is the determinant of A then? It is AD minus BC. If the determinant of A, that is denoted by this, if this determinant is 0, then it is a singular matrix. And for singular matrix, A inverse is not defined. And then if the determinant of A is non-zero, then we have this matrix to be as a non-singular matrix. So for non-singular matrix, determinant comes out to be non-zero. And for non-singular matrix, A inverse is defined. A inverse exists. Second remark, suppose A matrix is post multiplied by B, or B is pre-multiplied by A. So this will refer to the product AB. Right? This is the product AB. Now let's move on to the theorems. First theorem is, if A is an m by n matrix such that this B is obtained from A by applying this row operation R, then prove that there exists a non-singular matrix P such that PA is equal to B. So for the proof, now since it is given to us that B is obtained from A by applying the row operations, right? And suppose we have applied the row operations, few row operations, and we get for the first any row operation, and for the first row operation we get the elementary row matrix to be as E1. For the second row operation, if I apply, then I get the elementary row matrix as E2, and so on. I get all the matrix as ER. If the number of row operations I apply to be as R, right? And suppose that corresponds to pre-multiplication by the elementary row matrices, all these. Because we are going to prove that PA is equal to B. So P is before A, right? So in case of this, we are going to apply the pre-multiplications of the matrices, right? So suppose that corresponds to pre-multiplication by the elementary row matrices. These are your elementary row matrices E1, E2, ER, right? So E1, E2, E3 up to ER. If you now pre-multiplication is the product of these matrices. When you take the product of these matrices, you will obtain a single matrix, right? Whenever you take the product of the matrices, you will get a single matrix at the end, right? So thus I'm taking this B to be equal to, because B is obtained by applying the row operations on A. So we write B is equal to I have applied the row operation, so E1, E2, the products, E4 up to ER, right? And then multiplying this product with A. This product is your single matrix, and let me denote that with P, where P is equal to the product of elementary row matrices up to ER. Now since each of these E1, E2, E3 up to ER, these are always non-singular matrices. So since E1, E2, E3 up to ER are non-singular, so therefore this P is also non-singular. Yes, P is equal to the product of these matrices, so therefore P is also non-singular. Hence there exists a non-singular matrix P such that PA is equal to